All right, hey people watching this. This is 3 notes for Calc. I'm going to backtrack a little bit and go over the little bit of stuff that we went over yesterday. So here is this. Finding limits analytically. That is not using a graph, but I'm going to graph a lot of these just so that you can kind of make that connection. But analytically is just by like using different strategies to try to be able to evaluate limits. Now, typically you want to always do this first. Plug it in. Okay, try to plug in the limit and find the y coordinate based off of that. And if you can, then you're done. Then you don't have to do anything special. Okay, so like down here, we have some examples and we have like the limit as x goes to 2 of 3. Okay, that is like 3, like y equals 3 is that equation. So we said that the graph looks like this. And we're trying to evaluate the y coordinate or the limit at 2. So this is 2 comma something. We just have to figure out the y coordinate. Well, it's obviously going to be 3 because it's all the way across. Number 2 is the limit as x goes to -4 of just x. Now keep in mind that's like y equals x, and if I would graph that, I would go through, and y equals x is a line that looks like this, and so we're looking specifically at an x coordinate of -4. We're trying to find the y coordinate. That's the limit, okay? -4 would be at -4. Now, otherwise, just looking at the equation, so that makes sense according to the graph, but just take this thing and you plug -4 in, and that's your limit, right? -4 plugged in for x is going to be -4, of course, right? Yeah? Okay, what's up?
So you just plug that number.
You just plug that number in.
So
You always try to plug, yep, you plug that number into the equation. So you plug whatever your limit is approaching in for your thing. You did the same thing over here. You plug 2 in for this equation. Well, there's no x for me to plug into, so you just evaluate it and it's 3, right? So the next one. The next one, you just plug 2 into that equation. It's x squared, so that would be 2 squared, which is 4. So the limit's going to be 4. It's the y coordinate, right? We plug it in. Y equals x squared is a parabola. Y equals x squared is a parabola. That doesn't go along with this. So erase that from your brain. That's not the right graph. But anyway, y squared is a parabola, and they're just asking for the y coordinate at an x coordinate of 2, which would be 4. Okay, so you always try to plug stuff in. Now, I think it's a little bit stupid that you should be able to use direct substitution, because the whole purpose of using limits is to find y coordinates when they don't exist, right? Like I want to be able to try to find a y coordinate when there's a hole there, right? Like I want to be able to find that. I want to find a y coordinate when there's a vertical asymptote there. Like I want to be able to find that. If I can find the limit by direct substitution, that means it has a y coordinate already. So like there's no reason for me to have to find a limit there because like it already has a y coordinate. So I think it's a little bit silly that direct substitution even exists, but that's a thing. So always try to plug stuff in. So these 4 problems that we did yesterday, we just plugged the numbers in, right? 4x squared plus 3 is just a parabola. He's not going to have any holes, any jumps, any skips, any vertical asymptotes, anything. So he's going to be okay. Now, the second one will have a vertical asymptote. We said the domain is that x can't be -1, right? X plus 1 is the bottom. But that's not where I'm looking for my limit at. I'm looking for a limit at +1. And I can plug +1 in, and when you do that, you get 2. Okay? So even though that one does have some funny business, that's not where I'm trying to evaluate the limit at. So that one's okay. The next one is a square root, which looks like this. If I were trying to evaluate the square root over here, where like the graph doesn't exist, then I couldn't do it and the limit would not exist. But I'm trying to evaluate at 0, which is here, and it has, if I plug it in, I find that the y coordinate is 2. Okay, this one is another, oh no, this is a cubic root. So he does go left and right in every direction, no holes, no vase, no nothing. If you plug the number in, you get the cubic root of 8 or 2. Okay, so always try to plug it in. That's your first strategy. Strategy number 1, plug it in. Always try to do that. I know that we will get to the test and I will put problems in front of you, and a bunch of them, like 90% of the problems on the test is like, find the limit of this, find the limit of this, find the limit of this. And you will get so bogged down into like, oh my gosh, what strategy do I use? Like, how do I figure that out? That you'll forget to plug it in, and that's all you need to do is just plug the dang thing in and you'll get an answer, right? So always try to do that as your first resort. Plug the number in, okay? All right, second strategy is when you have stuff that are, this is 4 vase or holes, okay? So 4 vase or holes, like in this problem right here, I have a va, or maybe it's even a hole, I don't know for sure, at 1. So I am not allowed to plug 1 in, because if I do that in the bottom, then it's not going to work, right? Like I want to be able to plug 1 in there, but if I do that, then I'll end up with 0 on the bottom, and I can't do that, okay? So strategy number 2. Number 2 is divide. I'm going to say or factor. Factoring and dividing are kind of similar to each other because you're just basically getting rid of stuff, okay? So I'm going to either try to divide or I'm trying to factor, okay? So I've already showed this to, I showed this to Kyle. Kyle knows how to do this, and maybe I like hinted the other day. But what I want to do is I want to be able to like break down this top so that whatever he breaks down into, I can cancel this x minus 1 with an x minus 1 on the top here, hoping that those cancel. And then basically my denominator is gone, and whatever's left over, I can plug that 1 into. Does that make sense? Okay. Now, x cubed minus 1 does, in fact, break down. Okay. But I don't know what it breaks down to be. So what I'm going to do is I'm going to do some long division. Or do you want to do synthetic? We can do synthetic. Do you want to do synthetic division? No, you want to do long division? Yes, sure. Synthetic division. Okay, so I am taking, and this is what I'm dividing. I'm taking this thing, which is x cubed plus 0x squared plus 0x minus 1, yeah? And I am dividing that by x minus 1. That's what we're doing, right? Okay, just to put the zeros in. So let's do some synthetic. We can get away with synthetic because we're dividing by x minus 1. So that works, right? Okay, so we're going to divide it out, and we're going to see what's left over. So 1 goes on the outside, right? Positive 1, yeah? Okay, then my coefficients are going to be 1, 0, 0, negative 1, yeah? Okay, now I just do my division. Okay, 1 pops down, multiply, add, that would be 1 again, multiply 1, add, that would be 1 again, multiply 1, and that would be 0. So that's my remainder. So it does go in there evenly because I have 0 as a remainder. Okay, what does this thing look like?
1x squared plus 1x plus 1.
X squared plus x plus 1. Yeah, 1x squared plus 1x plus 1. So what this means is that this thing right here, x cubed minus 1, divides out and is equivalent to x squared plus x plus 1. It divides out. Like it's gone now. So for all intents and purposes, I can evaluate the limit of this thing instead of evaluating the limit here, right? Like, because that's what it divided out is. Like, that's what it simplified is. So, am I allowed to plug 1 into this thing? Mm-hmm. Sure, his domain is all reals. I don't have any problems there. I can just plug the number 1 in. So 1 squared plus 1 is going to be 3. The limit there is 3, okay? So that's the second strategy. If you can't just plug the number in, try dividing or factoring it to get rid of that little hole or whatever it is there. And if it works, then just plug the answer in or plug the limit in from there to what you have left over. Make sense? Okay? Yeah. All right, there we go. Okay? Strategy for finding limits, we'll go through these here in a second. But I'm going to go, and while we're on the dividing out technique, I'm going to go over this example, and then we'll go back up. Okay? So this is on the back page. This thing right here is what we're trying to evaluate the limit at negative 3. Can I just get away with plugging negative 3 in? No, because negative 3 on the bottom is going to end up giving me 0. But what I'm going to do is I can either divide it, or this one breaks down really nicely into a simple trinomial on the top, right?
If it was negative 2, could you divide it?
If I was trying to find the limit as x goes to negative 2, yes. Yep. If that was the limit as x goes to like negative 2 or something other than negative 3, I could totally plug it in. Because the only problem I have is at negative 3. So, like, even though it has a something problem at negative 3, if I'm not plugging in at negative 3, that I don't care, right? But we'll have to do something different here because we are plugging in at negative 3. What multiplies to get negative 6 but adds to get positive 1?
3 minus 2.
Positive 3 minus 2. Okay, so the way that this works is that x plus 3 can cancel out of the top and the bottom. So what this simplifies to be is the limit as x goes to negative 3 of just x minus 2. Right, like that whole thing simplifies to be x minus 2 after I've crossed everything off that I need to. Mm-hmm. And now can you plug negative 3 in? Sure, and you get, so the limit or the y coordinate, if there was a y coordinate, there's not because there's a hole here, right? This means that there's a hole, right? Hole. If there's a hole, like that hole's y coordinate should have been negative 5, right? It doesn't actually exist because it's a hole, but if there was a y coordinate there, it would have been at -5. Okay, now, one thing I want you to write down in your notes is this, because they'll use this terminology, I think, on your homework assignment or later on. A hole is considered to be a removable discontinuity. That's a big word. A removable discontinuity. So a hole is discontinuous, right? It like is not continuous at that spot because there's a hole there, right? It like drops out at that spot. Okay, so it's discontinuous. But because the hole cancels in the top and the bottom, it is considered to be removable because you can like get rid of it, right? Like I could still evaluate the limit, right? Was this one that we divided out here, was that a removable discontinuity?
Mm-hmm.
Sure, like I was able to remove the x minus 1, so that 1 was a removable discontinuity. I was able to divide it out, okay, so they'll use that. So that means I had a hole at x equals 1, okay, because I was able to remove it. All right, so strategies, let's go back up to strategies. Learn to recognize when you can just use direct substitution. That's number 1, that's what you need to do first. Number 2, if the limit cannot be evaluated by direct substitution, try to find a function that agrees with f for all other functions, which just means either divide it out or factor it so that you can get rid of that one place where it's not agreeing with it. Okay, so divide or factor, that's number 2. That's the process. Okay. Number 3 is apply theorem 3.6 to conclude analytically that blah, blah, blah. This is what we're going to learn next, okay? So this one, number 2 is the divide out or factor process. Number 3 is going to be the rationalizing technique, and I'm going to show you how that works here in a second, okay? So number 3, apply theorem 3.6. You don't know what theorem 3.6 is? Let's see, is theorem 3.6? 3.6 right here. Theorem 3.6.
Postulate stuff.
What? No.
So it's
Don't worry about theorem 3.6. I'm going to show you what it looks like.
No,
But theorem
like,
3.6
on the
is
test.
rationalizing. What?
on the test you're gonna have to put like
No, no.
3, 2.
Nope. Nope, you don't have to like give reasons or anything like that.
Good.
Okay, so number 3 is rationalizing. R-A-T-I-O. Ooh. R-A-T-I-O-N-A-L-I-Z-E. Rationalize. The rationalize technique. I'll show you that here in a second. But number 4 is using a graph or a table to actually solve your thing. So if all else fails, graph the thing and look at what it looks like, okay? All right, here's the rationalize technique. You know that you need to rationalize if you have a square root in there. This is like the key right here. Ding, 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 ding. When it has one of those, you're probably going to end up rationalizing, and it's going to end up being really super nice. Okay, do you remember when we would rationalize before?
If there's a square root in the bottom.
If there's a square root in the bottom, so like if you had like 3 over the square root of 2, right? You would multiply by the square root of 2 over the square root of 2, right? Okay. Or let's say we had 3 over 2 plus I. That's another way we would rationalize. We would multiply by 2 minus I over 2 minus I, right? We would do the conjugate, okay? So those are ways of rationalizing. That's rationalizing that we've done in the past. This one is going to look a little foreign because we're not rationalizing the denominator. Here we're rationalizing the numerator. Okay, so what we're going to do is we're going to focus on the square root on the top, and we are going to rationalize based on that. So what I'm going to do is I'm going to multiply by the square root of x plus 1 plus 1, okay, instead of x plus 1 minus 1. I'm going to switch this minus to be a plus, okay? But what I do to the top, I have to also do to the bottom, so I've got to do that, plus 1, okay? So these two are like conjugates of each other. If you need to, like, conjugates. They still are conjugates of one another because you're just making one of them plus and one of them minus, okay? So same process again, and it's going to end up like falling out really nicely. Okay, happy with that? Are we ready? Ready for this process? To multiply the top, we still will have to FOIL. You see how that FOIL happens? Like this is one piece right here and the minus 1 is another piece, right? This is one piece and the minus 1 is another piece. So we're going to have to FOIL. You see that? Those are my chunks. Okay, So here's the deal. It's gonna be ugly to begin with, but it's gonna be nice to end with. Okay. So the first thing that we're multiplying is these two square roots. The square root of x plus 1 times the square root of x plus 1
X plus 1 squared.
is the square root of x plus 1 squared. It's like this thing.
Oh.
Okay. But what's the square root of x plus 1 squared?
Just X plus
Just x plus 1. It ends up falling out of that square root. Does that make sense?
Yeah.
Okay, so when I multiply the two square roots together, because they're the same, it ends up being just x plus 1. Yeah? Is that little box in the bottom bothering you?
No.
No? Okay. All right, then the next thing we multiply
X plus 1.
is the square root of x plus 1. I take this guy times the positive 1. Okay? So the square root of x plus 1 times 1 is just the square root of x plus 1. Yeah? That's my second piece. So first piece, second piece. Then I'll have a third piece and a fourth piece. Okay? Then I do negative 1 times the square root of x plus 1. That's my inside pieces. But that's going to be negative square root of x plus 1. Oh, look at that. Just like what normally is supposed to happen, those two middle pieces are going to cancel out. And then I take negative 1 times positive 1. Yeah? Which is minus 1. Okay, this is going to be nice, folks. This is going to be real nice. Okay, so that's all my top stuff. Okay, now the bottom. I'm going to put a little note here. Don't distribute.
Why not?
Because I'm going to show you how it happens. Really nice. Don't try to distribute that x through. What we're going to do is we're going to leave this x right here times x plus 1. We're going to like cheat and just write them like that side by side. Because I'll show you what happens in a second. Yep, I'm sure. I don't want to distribute that x through. I don't want to do it. I don't want to do it. Okay, good. We're just going to write it like that. All right, let's simplify the top. Don't distribute that bottom through.
X.
Equals. So I have this thing cancels with this thing. And then the plus 1 cancels with the minus 1. So on the top, all I have is x. On the bottom, I still have all that junk. Do you see now why I don't want to distribute it through? How's come? The x's are going to cancel now, right? It's more obvious to see that those x's cancel now. Okay. All right, we're so close to being done. Okay, after you cancel those x's, what's left on top?
0.
1. 1 will be left on top, yep. And then the square root of x plus 1 and then plus 1. Will these two 1s cancel?
No.
No, how's come?
They're connected.
This is trapped with a plus sign. Okay, so this is all the simplification that we can do, right?
That's weird.
And now we have to evaluate the limit. So I want to do the limit as x goes to 0 of this thing. 1 over the square root of x plus 1 plus 1. Right? I want to do that.
Is plug 0 in.
Now can I plug 0 in and have it be legal?
Wouldn't there be a domainer in the bottom?
But after I get it looking like that, it won't end up being 0 on the bottom here. Right? Like the square root of 0 plus 1. This is the square root of 1 plus 1. Well, the square root of 1 is just 1 plus 1. So
Oh,
that's
I
2
get
on
it.
the bottom. So the limit will be 1/2 when you plug it in, right?
That was kind of. So the problem before was not square
The
root,
problem
it was
before, I
0.
could not plug 0 in because if I
Then
plug
I would
0
have
in, we
0.
didn't check that. But if we plug 0 in, we would end up 0 on the bottom right away, and that would be bad, right? But by multiplying by the conjugate of the top, we ended up getting it to a point where I could plug 0 in and it's not going to be
So the
a
only
So if the
problem.
limit was like,
What?
if the limit was like 1, I could have plugged it in without
Right,
doing
yes,
all that.
right.
So the only reason that you would need to do all that hard work is if the limit that you're plugging in gives you an error.
Yes,
I don't know how to do 13.
correct. So there's that. So the limit there is 1/2 because you get it to a point where it's an equal function, like it's the same as it was before, but just in a different form. We just change the form of it by multiplying by the conjugate, okay?
When you rationalize, will there always be like that extra part outside of the?
And that can cancel with the bottom, yes. Yep. So the limit there is 1/2. If there was a y coordinate, which there's not, it's like it's probably a vertical asymptote at that place. But if there was a y coordinate there, it would have been 1/2. Okay? Does that make sense? Okay, which question did you say? So that's strategy number 3 is rationalize. If all of them fail, which sometimes you cannot do any strategy. Like there is no strategy. Sometimes like none of those options work. If none of those options work, graph it. Or use a table. Like kind of like we did yesterday. We used a table as part of your homework assignment. Do the table thing. Figure out what it's approaching, right? Do one of those things. I know, it's kind of unpleasant. You wouldn't have to do the whole table. You could just do these middle two, right? Like a couple of people said that. Just do those middle two and do numbers that are really, really, really close on either side and see what it's approaching, right? So if everything else fails, graph it or use a table to figure out what that y coordinate should have been.
Can we do 13?
Sure. What does 13 ask?
What we just did, but it has a square
We're
root
at
instead of like a 1.
Where are we at here? Properties of continuity. That's not my one. Am I in the wrong spot? I don't have the 3-3 homework.
Do you want to scan it?
I don't know. I should have it. Where
pretty empty.
did it go?
It's gone.
3-3. That might be at the very, very end, maybe. Chapter 3 review. Nope. Nope. Oh. Nope. It's not there. Shoot. Can I scan? I might have. Oh, I have the review right here. Okay. Scan. Okay. Alright. 13. You said that one?